In this section of the video series, we are going to prove a theorem concerning the order of growth of theta of x and psi of x. We will show that they are of order x. Remember, as I stated from the beginning, a here is always an unspecified constant. And throughout this video series, we always use the same labeling as in Hardest book. Now recall, from the previous section of the video series, we established the following relation between psi of x and theta of x. Therefore, in view of the theorem for 13, this suffices to show theta of x has an upper bound that is a multiple of x, and psi of x has a lower bound that is also a multiple of x. Of course, those two a's are not the same, but unspecified constant. You can see immediately, once we established these two relations, then because the difference between psi of x and theta of x is a term that grows slower than x as x goes to infinity, we will establish both of these relations. Let us establish the first inequality. And more precisely, we will show the following. And we will write this as a theorem for 15, which states that theta of n is less than twice of n times log of 2 for all n greater or equal to 1. So here, the constant in front of n will be 2 times log of 2. And it follows from this statement, you see in this statement, n is a discrete variable. It is for all positive integers. Now, how to turn this into the continuous variable? For a continuous variable x, theta of x, but the monotonicity of theta is always less than or equal to the theta of the ceiling of x, the smallest positive integer bigger than x. Here x is always a number bigger or equal to 2. And this guy is an integer. So, by our theorem for 15, we have this term less than twice of the ceiling times log of 2. And now, by the property of the ceiling function, this is less than 2x plus 2 log of 2, which is less than or equal to 4x log of 2. And this part is true whenever x is bigger or equal to 1. We're not trying to find the most optimal choice for a. So now you see, in order to establish this equation, now you see it suffices for us to consider the discrete variable case. Now how do we prove theorem 415? The proof is done by induction on the variable n. And suppose, first, if n is equal to 1 or n is equal to 2, then the statement is trivial. Because by definition of theta, theta of 1 is 0. And the theta of 2, because 2 is a prime number, is equal to log of 2, which is also less than 2 times log 2. Now, suppose the statement is true for all n less than or equal to n naught minus 1. And we are going to prove this statement for n equal to n naught. And that completes the mathematical induction. And now we'll divide the proof based on the parity of n naught. If n naught is even, and n naught bigger than 2, because we have already seen trivially that when n is equal to 2, we have this inequality. So now let's focus on a case when n naught is bigger than 2. Then, if you look at theta of n's definition, by definition, this is a summation of log of p's, where p is a prime number less than n naught. Now, because n is an even number, and an even number bigger than 2 is never a prime. So, the sum is also equal to the summation for all prime numbers less than or equal to n naught minus 1 of log of p's. So this is because n as an even integer is not a prime number. And now we are ready to use the induction hypothesis. By the induction hypothesis, this is less than or equal to twice of n naught minus 1 times log of 2, which is less than twice of n naught times log of 2. And this completes the proof when n naught is even. Now, what happens when n naught is odd? If n naught is odd, say n naught is equal to 2m plus 1. And now we have theta of n naught is equal to theta of 2m plus 1. And now comes a very tricky step. So this is a very tricky step in the proof. We're going to split this theta of 2m plus 1 in two parts. And now, because m plus n now will be less than n naught, therefore, the induction hypothesis applies to this part. By induction hypothesis, we shall abbreviate as IH, theta of m plus 1 is less than or equal to twice of m plus 1 times log of 2. So it suffices to give a good bound for this difference. Now, how to bound this difference? This difference, by definition, is a summation of log p when p ranges from m plus 2 all the way to 2m plus 1. So p is bigger than m plus 1, less than or equal to 2m plus 1. And you can write this as a product. So this will be log of the product for p bigger than m plus 1, less than or equal to 2m plus 1. And now the rest of the proof involves a little combinatorics. Combinatorics is tricky but elementary. Now we make the following claim. We claim that this product divides the combinatorial coefficient 2m plus 1 choose m, which is also 2m plus 1 choose m plus 1. By definition, this is a product from m plus 1 to 2m plus 1 divided by m factorial. Remember, I assume the audience are familiar with the binomial theorem, including those binomial coefficients. Now, why is this claim true? This claim is true because each prime p from m plus 2 to 2m plus 1 divides the product from m plus 2 to 2m plus 1. And by the elementary number theory, and in particular by the unique factorization theorem of integers, we know that these distinct primes must also divide this whole product, given that each factor divides some of them. But at the same time, because p starts from m plus 2, each factor must be coprime to the m factorial in the denominator. So this claim follows. And in particular, it follows from this claim that if this product divides this binomial coefficient, then we have it must be less than or equal to it. So this is a classical trick of number theories. To show that one integer is less than or equal to another, you show the first integer actually divides the second. And now you look at this binomial coefficient. We claim that this guy is less than or equal to half of 2 to the 2m plus 1, which is simply 2 to the 2m. And why is this true? This is true because in the binomial expansion of 1 plus 1, 2, which is equal to 2 to the 2m plus 1, in the binomial expansion of this, the term 2m plus 1 divided by m appears actually twice. Once in this form, once as just 2m plus 1 choose m, and once as 2m plus 1 choose m plus 1. And you know they are actually equal. So this guy appears twice. And in particular, twice of this guy is less than 2 to the 2m plus 1. So one of them is less than or equal to this guy divided by 2. This explains this inequality. So now we have established that this product is less than or equal to 2 to the 2m. And the only thing that we are left to do is to plug in this inequality back to this parenthesis. And you will see the difference between those two thetas is less than or equal to log of 2 to the 2m. Which is equal to 2m times log of 2. And thus, theta of 2m plus 1, by this splitting trick, is less than or equal to 2m times log of 2 plus, and remember, this part was bounded by the induction hypothesis. And this is equal to twice of n naught times log of 2. And therefore, we are done with the proof of theorem 415. The proof is a bit tricky. First, we use induction on n, and it divided into two cases based on whether the number is even or odd. The even case is relatively easier, but the odd part is quite involved. We use this separation trick and try to find an upper bound for this product, the product of prime numbers. And that upper bound is established by finding something that is, on one hand, divisible by this product, on the other hand, bounded above by some power of 2, where we seriously used the binomial theorem and the binomial coefficients. For beginners, it's really difficult to think of such a proof.